When I was discussing independence and the definition of independence and what two probabilities you need to check to see if two events are independent, if the probability of survived given first class is the same as the probability of survived, then those events would be independent. Or the other way around, if the probability of first class given survived is the same as the probability of first class, then the events would be independent. But if those probabilities are not equal, then they're not independent. So I gave you an example of not independent. Here's an example of something that is independent, or probabilities that show us that two events are independent. Suppose we have the following probabilities for a large population of college students. The probability of a student being male is 0.6. The probability of a student being a smoker is 0.15. And the probability that someone is a male and a smoker is 0.09. From this, we can calculate the probability that someone is a smoker given that they're male. Using our formula, probability that they're a smoker given that they're a male is the probability that they're a smoker and male divided by the probability that they're a male. Notice again that this probability that comes after the vertical bar, that's what's in the denominator. Smoker and male is 0.09. Male is 0.6. Divide those two, you get 0.15. So you see that the probability of smoker given that the person is male is equal to 0.15, which is also the probability that the person is a smoker. So the events male and smoker in this case are independent because smoker given male is the same probability as smoker. And to look at that in another location, when we were talking about the multiplication rule, so if we check the multiplication rule for independent events, we can use that to see if the events are independent. So we want to know, is the probability of male and smoker the same as the probability of male times the probability of smoker? Because if it is, then we have the probability of A and B is equal to the probability of A times the probability of B, which will only happen if the events are independent. So we check, is 0.09 equal to 0.6 times 0.15? Probability of male 0.6, probability of smoker 0.15. We multiply those two, and sure enough we get 0.09. So since this and probability is simply the product of these two probabilities, that means those two events are independent. That doesn't happen that often, but I wanted to show you an example of that. Then I wanted to look at a problem from the homework, maybe a couple problems from the homework. So this problem says, let A be the probability that a student has a Visa card, and they tell us that probability is 0.6. Let B be the probability that the student has a MasterCard, and they tell us that that probability is 0.4. And then let C be the probability that they have an American Express, and that probability is 0.2. And then they give us some joint probabilities. They say A and B is 0.3. They say A and C is 0.11. They say B and C is 0.1, and they say A and B and C is 0.07. And then the first question is, what is the probability that the selected student has at least one of the three types of cards? So that would be the probability of A or B or C. And earlier in the notes, I gave you a formula for such a thing, even though that's a little bit, I mentioned at the time that this is a little bit ugly when you get more than two events. So, just move this down a little bit. The probability of A or B or C is the probability of A plus the probability of B, et cetera, et cetera, et cetera. So, but all of these numbers we were told, that's 0.6, probability of B, 0.4, probability of C, 0.2, then subtract probability of A and B, 0.3, and then subtract probability of A and C, and then subtract probability of B and C, and then add the probability of A and B and C. So 0.6, it's not 6.6, no, 0.6, no, 0.6 plus 0.4 plus 0.2 minus 0.3 minus 0.11 minus 0.1 plus 0.07, 0.76, which is exactly the answer they have here. So that's just a straightforward use of this kind of weird, unusual formula. Okay, now the next one's even tougher. What's the probability that the selected student has a Visa and a MasterCard, but not an American Express? So they're saying, what's the probability the student has a Visa and a MasterCard and not an American Express? Like that. So this is a little bit tricky. There's a rule referred to as total probability, or the total probability theorem, something along those lines, which says something like this. The probability of A is the probability of A and B plus the probability of A and not B. In other words, B either happens or it doesn't. So when A happens, A either occurs with B or A occurs with not B. So if you take that general rule and we apply that with different names, so everywhere the A is in this rule, we're going to replace it with A and B. Like this. And then where we have B up here, we're going to make that now this third event C. And then similarly, the B complement is going to be the C complement. Okay, so now what's interesting about this last line is probability of A and B, we were told that's 0.3. The probability of A and B and C, we were told, that's 0.7. The probability of A and B and not C, that's what we're trying to find on this particular problem. And so if we subtract 0.7 from both sides, we will get that the probability of A and B and not C is going to be 0.23. Don't think I need this highlighting anymore. Another way of visualizing this, I did something on Desmos that might help. So if we're just looking at event A and event B, and we were told that A and B is 0.3, so I put a little 0.3 there. Now, if we bring event C into the mix, we see this 0.3 that was this overlapping region here. That 0.3 is now split into two pieces. One piece that's 0.23 and one piece that's 0.07. And so the piece that's 0.23 is in circle A and in circle B, but not in circle C. So that piece right there is A and B and not C. And so that's the 0.23 that we just calculated. The next parts, calculate B given A and A given B. That's fairly straightforward because we have formulas for that. So the probability of B given A, we have a formula that says that's the probability of B and A divided by the probability of A. And the probability of B and A, once again, we were told, expand this a little bit, probability of B and A, we were told, is 0.3, and the probability of A is 0.6. Divide those two and you get 0.5, which you can see right there is that answer. And then for the probability of A given B, that's the probability of A and B divided by the probability of B. So the numerator is still 0.3, but now the denominator is B, which is 0.4 probability, and you divide those two, and now you get 0.75, which is this answer that you see right here. The interpretation part I'll skip. If we learn that the selected student has an American Express card, what's the probability that he or she also has a Visa or a MasterCard? The next part says if we learn the selected student has an American Express card, so you could say given that they have an American Express card, what is the probability that he or she also has both Visa and MasterCard? So we can write this like this. What is the probability that they have Visa and MasterCard given that we know they have an American Express? Well, that's the probability of A and B and C divided by the probability of what's after the vertical bar, which is C. And they told us both of those. The probability of A and B and C is 0.07, and the probability of C is 0.2, and you divide those two and you get 0.35, which you see as this answer right here. And then this last part, given that the selected student has an American Express card, what is the probability that he or she has at least one of the other two cards? So this is very similar, except it's what is the probability, what is the probability of A or B given that they have an American Express card? So that's the probability of A or B and C divided by the probability of C. So now we got to figure out this. What is the probability of A or B and C? And to help see this, let's go back to the Venn diagram. A or B and C. So A or B intersect C. And I've added a couple new numbers to the Venn diagram. A and C was 0.11. So you see these two numbers here add up to 0.11. B and C was 0.1. Let me just double check. Yeah, B and C was 0.1. So you see these two numbers add up to 0.1. So what is in circle C that is also and in A or B? All three of these numbers are in circle C and either in A or B, which is this probability that I'm looking for right here. In circle C and either in A or B. That's all of those numbers. Those numbers added together add up to 0.14. And 0.14 divided by 0.2 is 0.70, which is exactly the answer you see here. So there's a lot of problems where a Venn diagram is kind of very important. Okay, this one I thought might be a little bit difficult. An aircraft seam requires 27 rivets. The seam will have to be reworked if any of the rivets are defective. Suppose rivets are defective independently of one another, each with the same probability. If 24% of the seams need reworking, what is the probability that a rivet is defective? So, let me make this a little bit smaller and we can possibly reason through this. So, the probability that a seam, the probability that the seam will have to be reworked, I'll just write that out, reworked, is 1 minus the probability that it's not reworked. Or I guess I could say reworked complement. Like that. Okay. So the reason why I'm doing complements here is I think I can figure out the probability that it's not reworked. It's not reworked if all rivets are okay. And since they're independent, that's the probability that a rivet is okay to the power 27. So the first rivet has to be okay, times the second rivet has to be okay, times the third rivet has to be okay, etc. All 27 rivets have to be okay. And if all 27 rivets are okay, then it does not need to be reworked. So I think this is the equation I want to set up. And now what they say is 24% of the seams need to be reworked. So if I redo this entire equation, then that 24% of the seams need to be reworked. So the probability that a seam needs to be reworked is 0.24. And now if I just rearrange this equation a little bit, you're going to see the probability that a rivet is okay to the 27th power is going to equal, this is 1 minus 0.24. And 1 minus 0.24 is 0.76. So now I have to take the 27th root of each side, probability that a rivet is okay is 0.76 to the 127th power. So I need parentheses around this. I need that whole thing to the power 127th. But luckily, we have calculators that will do such things. Okay, let's try this again. 0.76 to the power 127th. That's 0.9899, let's say, 9899. So 0.9899 is the probability that a rivet is okay. So therefore, the probability that a rivet is not okay is going to be 1 minus 0.9899. And That's 0.0101, which, if you look at the answer key, there's the 0.0101. So that one was a little bit weird with the exponents and a couple different uses of complements, but hopefully that will help you get some of the more that'll help you get through some of the more difficult problems on the assignment. And just email me if you have any questions.